Good morning everyone. Today, we will be discussing the factors that affect resistance in conductors. We will be exploring how length, resistivity, and diameter can influence resistance, and present a solution to a problem related to this concept. Let's get started. Resistance to an electric current is a physical property of materials that can be impacted by a range of factors including temperature, length and area of the material, and the type of material. Different materials feature different levels of resistance to electrical current. Moreover, temperature and length of the material can additionally affect the electrical current as it passes through the material. Gaining knowledge about resistance and the factors that affect it can aid engineers to devise more efficient electrical solutions. Resistance in a conductor is directly proportional to its length. In other words, the longer the wire, the higher the resistance, and the shorter the wire, the lower the resistance. For a uniform wire, resistance is determined by the length of the wire, which is represented by the letter L. Therefore, the equation R is directly proportional to L is true. Resistance, R, of a conductor is dependent on its length, L, and diameter. This equation demonstrates the relation between resistance, R, and length, L, of two conductors. Resistance of the first conductor, R1, is divided by the resistance of the second conductor, R2, which is in turn divided by the length of the first conductor, L1, divided by the length of the second conductor, L2. This equation can be employed to determine the resistance of two conductors. Resistivity of a material is strongly affected by its physical and chemical properties. Metals tend to have their resistivity decrease with increasing temperature, which is attributed to the increased mobility of electrons. On the other hand, insulators tend to have their resistivity increase with temperature. Additionally, resistivity can be affected by concentration, frequency, applied voltage and pressure. The volume control of your radio is a variable resistor which alters the amount of current passing through the circuit when the resistance is changed by turning the volume control knob. This will affect the sound that comes from the speaker, and can range from soft to loud. Having an understanding of the elements that affect resistance can help us design circuits in order to be more efficient. The diameter of a conductor plays an important role when determining its resistance. When the area of its cross-section increases, the resistance decreases, creating an inverse correlation between diameter and resistance. In other words, thin wires have higher resistance whereas thicker wires have lower resistance. The cross-sectional area is one of several factors that can influence resistance. Doubling the area effectively doubles the number of electrons that can flow through, resulting in a doubling of the current. This relationship has major implications on the design of electrical components. When it comes to electrical resistance, the size of the wires used plays a major role. Wires with a smaller diameter have more surface area when grouped together, and a lower gauge number indicates they are thicker. As a consequence, the thicker wire has less resistance, thus it is essential to take into account the gauge number when calculating the electrical resistance for a project. The diameter of an iron wire conductor directly affects its resistance. For example, for a wire of 0.8 mm diameter, the resistance is 0.4 ohms omega. Thus, to calculate the resistance of a wire of 0.4 mm diameter, we must take the inverse of the proportional relation between the wire diameter and the resistance. This would give the resistance as 0.8 ohms omega. The resistance of a material is determined by two factors, the cross-sectional area and the length of the piece. Using the equation R1, R2 equals D2 squared, D1 to the power of 2, and the values of R1 equals 0.4 ohms, D1 equals 0.8 mm and D2 equals 0.4 mm, a result of R2 equals 1.60 ohms is yielded. This equation demonstrates that the larger the area or the longer the length, the greater the resistance. Understanding how temperature affects resistance is essential when designing and maintaining electrical circuits. The resistance of metallic conductors, such as copper, increases as the temperature rises, while semiconductors and insulators have a decrease in resistance as the temperature increases. Resistance is also impacted by temperature. As temperature rises, so does resistance. This connection is significant when dealing with electrical systems. Being aware of the temperature and how it affects resistance is key to ensure the efficient and secure functioning of electrical components. The 14th slide of the presentation is about the material that affects the resistance of a conductor. Here, the resistance is proportional to the resistivity of the material, or R equals L, with as a constant of proportionality. Variations in resistivity of the material cause a subsequent alteration in the resistance of the conductor. Being aware of the different materials and their resistivity enables us to compute resistance accurately. Resistors discussed in this slide have a constant resistance regardless of the temperature. The resistivity of the resistor, which influences the flow of current and resistance, is determined by the type of material. Electrical resistivity is an indication of how hard it is for an electrical current to pass through a material. This table shows that resistivities of materials can vary greatly. Silver has a resistivity of 1.6 x 10 to 8 Wm, while manganese has a resistivity of 1.84 x 10 to 6 Wm. Alloys have their own resistivity values, with constantan having a resistivity of 49 x 10 to 6 Wm and nichrome having a resistivity of 100 x 10 to 6 Wm. Insulators, such as glass, generally have resistivities ranging from 10 to the power of 10⁻10 to the power of 14 Wm. Resistance is calculated by dividing 1/2 the distance by the material's resistivity. In this example, the distance is 8.5 times 10 to the -4th meters, and the resistivity is 4.25 times 10 to the -4th meters, giving us a resistance of 1.41 times 10 to the -8 ohms. The area of the resistor can then be calculated by multiplying the radius squared by pi. Taking the radius to be 4.25 times 10 to the -4th meters, the area works out to 5.67 times 10 to the -7th square meters.